Okay, so this video is going to be in response to 3 questions that were posted in the wiki, and these are over problems 2, 4, and 5 on the homework. All right, so actually, as a matter of fact, let's separate this. Right, so here's problem 2. So problem 2 revolves, actually, most of this homework, okay, revolves around this equation right here, E equals h nu. And this is really the foundation of quantum mechanics. Okay, so we want to spend just a little bit of time here. This is the equation that Einstein basically, I hesitate to say discovered, but realized, I guess we should say. Okay, so what this equation says is that if I know the frequency of a photon, okay? If I know the frequency of the photon, a photon of light, that is, okay? If I know the frequency of a photon of light, then I can predict or calculate what its energy is, okay? And this is the birth of quantum mechanics because of this thing right here, okay? Planck's constant, what we call Planck's constant. And so energy can only come in discrete units of Planck's constant, right? So it cannot have any generic value. It must be in multiples of this number. In other words, it's quantized. Okay, so that's where the word that's where the phrase quantum mechanics come from. It means that energy is quantized. So let's talk about this word frequency real quick. Okay, so what is frequency? So frequency is the number of cycles per second that a phenomenon or some oscillatory system executes. Now, what does this mean? So let's say we have a wave. Let's look at a wave right here. And this wave, let's say this is a photon, right? And I'm looking at the electric fields oscillating up and down, okay? So the frequency would be the number of these crests that pass a specific point. So imagine the wave is moving to the right, right? And I count these number of crests that pass my location per second, okay? Or cycles per second. That is what frequency is. It's the number of cycles that a wave goes through per second. Okay, so that's what the wave is. So if I know that frequency and I know Planck's constant, I can calculate the energy. Now, we've already worked with energy in units of joules, right? We've already worked in energy in units of joules, and Planck's constant has this number in the SI system, okay? In the SI system, meters, kilograms, seconds, in that system, we use joules for energy, and it has this particular number, 6.63 times 10 to the negative 34. But there's a different way to think of energy, and we call that electron volts, okay? And that is the number of volts, right? So you have to go back to chapter 7, recall what a volt is, right? It's a unit of potential energy, electric potential energy. It's actually technically energy per unit charge, okay? But so what that means is, if I have an electron, I know what the charge on an electron is, and so if I accelerate it through a voltage, potential energy per unit charge, it being volts, multiplied by a charge, the charge on the electron, then I get energy, okay? And so that's what an electron volt is. It's the amount of energy that an electron would have if it is accelerated through some voltage, right? And frequency is measured in hertz, okay? Frequency is measured in hertz. So another way of writing Planck's constant is this 4.14 times 10 to the negative 14 electron volts per hertz, okay? So don't get too wrapped up in the units here. It's a little bit funky, but electron volts per cycles per second, okay? Energy per cycles per second is the units here. Now, okay, so what we want to do, we're given in this particular problem an electron of 0.511 MeV, right? And so I'll put that over here. So MeV stands for mega electron volts, okay? Stands for mega electron volts. And so mega meaning million, so I have 0.511 times 10 to the 6th electron volts. And so I'm going to put that right here, and then I'm just going to divide that. I'm going to use my equation and divide both sides by h to get the frequency. All right, now the main connection here, okay, the main connection here, and this is well, actually, I'll talk about that here in just a minute. Okay, I'll save that for here in just a minute. But this particular photon has an energy of 0.511 times 10 to the 6th eV. And it says that it's a gamma ray. Now, that doesn't really play too much role here, except what you can do is come up to this chart that's in your book, and you can look and see, okay, so we have electron energies, or I'm sorry, photon energies up here, and then here we have the frequencies, okay, the typical frequencies in these ranges for the different types of electromagnetic radiation. And down here we have the wavelengths. So one thing you can do, you can say, okay, this is a gamma ray. My answer should fall somewhere between something times 10 to the 20th up to about something times 10 to the 24. Okay, so for gamma rays, that's a very typical range, 10 to the 20th hertz, or 10 to the 20th cycles per second. 10 to the 20 of those crests will pass your point every second, okay, is what we're saying here. And your gamma ray frequency should fall within this range. So when you calculate that number, right, when you calculate this number, 0.511 times 10 to the 6th, divided by 4.14 times 10 to the negative 15, then you should get something that's in that range. Okay, so that's problem number 2. Problem number 3, problem number 4, actually. And I clicked on something that I definitely did not mean to. Okay, so problem number 4, all right? In your book, you're given this equation that says, okay, if I have an electron in an atomic orbit, right, some initial orbit, and then it drops down to a lower orbit, okay, these orbits are associated with specific energies, okay, these orbits are associated with specific energies. And as I drop from a high orbit to a low orbit, there's going to be a difference in energy between those two values, okay? And what that means is my atom can give off energy according to that difference, right? So if my electron starts at a higher energy level, E3, and it drops down to a lower energy level, E1, the electron will lose energy. And where does that energy go? It can go into a photon that is then emitted away from the atom. And we want to find the frequency of that photon. So we can just use this equation again. Energy is equal to HF. And here we have a delta energy, but it's still really an energy, right? It's still just an energy. It's a value of energy. It's the difference between two energy levels. And so you can still use this E equals HF equation and solve that for F to get the frequency. Right? Divide both sides by h. So that's problem number 4, right? Problem number 5, okay, this one takes you back just a little bit, okay? This one takes you back just a little bit, and that is that from chapter 8, okay, so once again, we're going to start with this definition of E equals HF, but if you recall from chapter 8, the wavelength of a photon multiplied by its frequency equals the speed of light, okay? So C equals lambda F. So for a photon, the speed of light is equal to the photon's wavelength times its frequency. So what this means is, actually I wanted to solve this equation for f. All right. So what this means is, what I can do is solve this equation for f and get c divided by lambda, and then I can plug that result in to my energy equation. So if I do that, then I'm going to get E is equal to H times C over lambda. But C over lambda is F, all right? So now that I've got C over lambda in my equation, E is equal to HC over lambda, I can solve this equation for the wavelength by dividing both sides by E and multiplying both sides by lambda. So there's your final result to get the wavelength, all right? So I hope that you found that helpful and beneficial, and we will talk to you guys next time. All right, have a good one.